First, I'd like to extend a big thank you to the organizers for the fantastic warm welcome here in Malang. I'm very pleased to be here, and it's a great privilege to get the opportunity to present some of our work on thermoelectric materials at this conference. So the title of my talk is about chalcogenide thermoelectric materials, and that's what I'd like to focus on for the most part in this talk, although I will not only restrict myself to chalcogenides, but I'll talk about oxides and some other materials as well. So I'll try and keep the talk fairly general and to give quite a broad overview of how I think the field of thermoelectric materials stands at the moment and what are some of the future prospects for these materials. So, if you please look at the screen to the left of me, I will try and use a laser pointer to point out some things on this screen here. I think it's more difficult to do on the screen behind me. So I'm from the University of Groningen in the Netherlands. Now, many of you probably have not heard of Groningen or don't know where it is. So we're in the Netherlands, this little country in the corner of Europe, and Groningen is up in the north of the Netherlands, quite close to the border with Germany. So I'm part of what's called the Zernike Institute for Advanced Materials. Next, please. So we're a materials science institute, quite a multidisciplinary institute, and it encompasses both physics and chemistry, as well as materials science and some biosciences as well. So we're quite multidisciplinary. A lot of our research themes overlap between these three areas. So we're quite international. We have around 40 professors from, I think, 25 or so different countries. And we currently have about 200 PhD students. So that's the kind of background I'm coming from. Next, please. So as I mentioned, I'm going to talk about thermoelectric materials today. And on this slide you can see an introduction to the thermoelectric effect and basically what it's all about. So the basic principle here is that if you have a semiconductor and on one side of the semiconductor you expose it to a heat source, and on the other side of the semiconductor you have a cold side, then the carriers, whether they are electrons in an N-type semiconductor or whether they are holes in a P-type semiconductor, will diffuse from the hot side to the cold side of the material. And if you have two semiconductor materials, one N-type and one P-type, and you link them up electrically, you can form a closed circuit and you can generate electrical power this way. So in other words, it's a way of power generation using a heat gradient. And this can be used as a form of energy harvesting, for example, to harvest waste heat from industrial processes or other sources. So I will mention a few thermoelectric applications a little later. On the bottom right of this slide is a picture of a thermoelectric generator. A lot of this technology is still in the prototype stage, so these are on rather small scale at the moment. This is a thermoelectric generator on the scale of a few centimeters in size. Next, please. So before I talk about the applications, we can ask ourselves what kind of materials are good thermoelectrics. So there are various physical properties that we have to consider. Now, the performance of a thermoelectric material is quantified by the so-called figure of merit, ZT. That's the equation at the top right of the slide here. ZT is dependent on various properties. First of all, the Seebeck coefficient, that's alpha in the equation up there. So that's basically the voltage that is generated in response to a certain temperature gradient over the material. So obviously the higher the voltage, the better in this case. The ZT is also proportional to the electric conductivity of the material. That's sigma in the equation up there. And finally, it's inversely proportional to the thermal conductivity of the material. So actually, the worse the material conducts heat, the better it is for thermoelectric applications. So kappa in this equation, which is comprised of both a lattice component and an electronic component, should be as low as possible. Now, unfortunately, these parameters cannot be optimized independently of each other, and they are actually counter-dependent on each other. And you can see that a little from the plot on the lower left there, which is carrier concentration of our semiconductor along the horizontal axis and ZT on the vertical axis. So in practice, the maximum ZT is achieved in the highly doped semiconductor regime for most materials. At lower carrier concentrations, the Seebeck coefficient is high, but the electrical conductivity is not good enough. And if you go to higher carrier concentrations, towards the metallic regime, then obviously the electrical conductivity improves, but the Seebeck coefficient decreases below optimum levels. So in the middle is where we want to be, usually in the narrowband semiconductor regime. Now in a thermoelectric device, the energy conversion efficiency is shown by the equation on the lower right there. So that's the quantity eta in the equation. And that is directly dependent on the thermoelectric figure of merit ZT. And we have the Carnot efficiency, which is a maximum theoretical energy conversion efficiency given by the quantity circled in green. So that's equal to the temperature gradient across the device divided by the temperature of the hot side. So that's the maximum theoretical conversion efficiency. And obviously, looking at that equation, you can see that ZT should be as high as possible to approach this maximum theoretical efficiency. Next, please. So before I go further, I'd like to say a couple of words about how we measure these thermoelectric properties in the lab. So I'm an experimentalist. This is of great importance to us, how we do it. Shown here is the equipment that we use for high temperature Seebeck coefficient and electrical resistivity measurements. So we have a sample of a few millimeters in size usually, and we contact the sample along one side with a pair of thermocouples. So these also serve as voltage probes when we do a 4-probe electrical resistivity determination. So on the top side of the material, we have a heater, so that's the hot side of the material. And the lower side of the material is kept a few degrees lower than on the hot side. The thermocouples measure the temperature difference between or across a certain known difference, a certain known length of the sample, and we measure using those thermocouples also the voltage that is generated in response to that temperature gradient. Simultaneously, we measure the electrical resistivity using a 4-probe measurement. Current is sourced from the electrode on the top side of the material, so flows across the material to the bottom side. And again, we're measuring the voltage using the 2 contacts in the center of the sample, so we can determine the resistivity simultaneously to the Seebeck coefficient. Next, please. Another critical quantity that we need to measure is thermal conductivity, and we actually measure thermal diffusivity directly. So we have a laser source, in this case a xenon laser. We illuminate one side of the sample with a laser flash, and we measure the temperature rise on the other side of the sample using a pyrometer. And we measure the rise of temperature with respect to time across a sample. So that gives us the thermal diffusivity, which is D in the equation shown there. What we want in the ZT formula is the value of thermal conductivity, which is kappa in the equation there, So we also need to know the material density, rho, and the specific heat, Cp. Then we can determine kappa, which is the quantity we want. I should mention that there's a lot of errors involved in these measurements, and the typical error bar on the measurement of kappa is something like 10 or 20%. So you should be careful when you see these results in the scientific literature. Usually people report these values as if it's exact, but it's not really. You should always bear in mind that there's a very large error bar in this. Next, please. So I'll mention now a few applications of thermoelectric materials. So thermoelectrics have been known for quite a long time, and they've been used in certain applications since the 1960s. But these have been very specialized niche applications, I would say. And that's because the efficiency of thermoelectric materials is basically not high enough currently for widespread commercial use. So, for example, thermoelectrics have been used in situations where other forms of power supply are not possible or not reliable. For example, in space science. NASA has been using thermoelectric power generators since the 1960s, and most recently on the Mars rovers, for example, Curiosity, they have thermoelectric power generators. So these use radioactive decay, so that they use the alpha decay of plutonium-238, which generates a lot of heat, and then they can couple that to a thermoelectric power generator, and it gives a stable, long-term power supply. So the designed lifetime on the Mars rovers is about 14 years of power supply, and initially they obtain 110 watts, which declines slightly over this 14-year period. Next, please. Other applications available at the moment are pretty specialized. For example, this is a wood-burning stove, which is available commercially, and it's coupled up to a USB port to power mobile devices. So these are very low power applications of the order of 10 watts or so. Next, please. There are other envisaged applications which I would say are more at the prototype stage at the moment. On the large scale, any sort of industry which generates a lot of waste heat could usefully benefit from thermoelectric energy recovery modules. So for example, at the University of Groningen we have a joint project just starting with Tata Steel. In their steel factory, they have molten steel, which is at about 600 or 700 degrees Celsius, and currently there's a lot of waste heat which is just being lost to the atmosphere. So it will be very useful if one can recover some of the energy from this waste heat. So we have a project to place prototype thermoelectric energy recovery modules directly above the molten steel, and to regain some of that wasted energy back in the form of electricity. Many automobile manufacturers have been considering putting waste heat recovery modules on their exhaust systems on vehicles. So again, those are at the prototype stage, and the best results so far are about a 5% increase in fuel efficiency. So it's not a huge amount at the moment. It's mainly due to the poor efficiencies of the basic materials themselves. But for example, if you're running trucks, commercial vehicles which are driving most of the day, every day, that can amount to quite substantial fuel savings over the course of the lifetime of the vehicle. Then there are solar cell applications, which again are at the prototype stage at the moment. So the idea here is to put a thermoelectric recovery module on the back side of the solar cell, so to combine it with the solar cell. So there you can also harvest some of the heat from the sun, as well as using the visible spectrum to generate energy. So again, I think those are not at the commercial stage yet, they're at the prototype development stage, and again, considerable improvements in the basic materials are still necessary. Next, please. So this is a plot from a review a few years ago, which kind of compares the energy conversion efficiency from thermoelectrics, so for different values of ZT, versus various conventional electricity generation schemes. So the current best ZTs are around 2. So that's the second lowest curve on the plot there. So you can see that solar energy or coal-powered electricity generation is far above what is possible with thermoelectrics at the moment. It's a bit of an open question as to how high ZT can go. People think it can maybe reach around 4 with further materials development, but that's a few years in the future currently. So we're currently around ZT equals 2. Next, please. So this is a similar plot showing efficiency on the vertical axis versus power level on the horizontal axis. And the S-shaped curve in that plot there is sort of for a general heat engine. So those are conventional power generation modules. And you can see for high power applications at powers of over around 100 watts, probably these conventional heat engines will always be better than thermoelectric materials. But there's a crossover point around 100 watts. And below that, thermoelectric materials, even in the current state today, are somewhat more efficient than these heat engine type generators. So it might be empowering large numbers of low power devices that thermoelectrics find their best applications. Next, please. So for example, you could use the heat generated integrated circuit technology to help generate small amounts of power. So maybe that would help in generating power in mobile devices. I should mention there's also a converse thermoelectric effect, which is known as the Peltier Effect. That's when if you apply a voltage to a thermoelectric material, you can generate a heat gradient. So you can put such a Peltier device on a hot spot in an integrated circuit and help to cool it. So in other words, using thermoelectrics as heat management devices in integrated circuits. So in large arrays of computational equipment, one might envisage local cooling devices and therefore eliminate the need for large-scale air conditioning, for example. There's also ideas of using thermoelectric power generation in medical implants. So if one could use simply body heat to power medical implants instead of having the need to replace batteries every few years, of course that would be a great advantage to patients. You could have medical implants with almost infinite lifetimes with regards to power. Next, please. So moving on now to one theory slide that I'd like to show about materials and how to make them better in terms of thermoelectric properties. So I apologize for the small writing and the equations on this slide. I'd just like to point out one or two things about the interdependency of thermoelectric properties. So if you look at the equation on the left-hand side for alpha there, it is dependent on basically two materials parameters which can be changed chemically. So first of all, the carrier concentration in the material, whether that's electrons or holes. So that can generally be controlled by doping the material with an impurity atom. And related to that, and related to the electronic band structure of the material, you can see that the Seebeck coefficient alpha is directly proportional to the carrier effective mass, m star, in that equation. So that's again to do with the electronic band structure of the material. On the lower left equation, we have the electrical conductivity. And you can see there that is inversely proportional to m star, the effective mass of the carriers. So you can see that's kind of running against the Seebeck coefficient, which is directly proportional to m star. And the electrical conductivity is directly proportional to n, the carrier concentration, whereas you have an inverse relationship for the Seebeck coefficient. So you can see there that the two properties, alpha and sigma, are kind of counter-indicated, and it is very difficult to optimize one at the expense of the other. So there is one parameter that can be somewhat independently tuned, and that's the thermal conductivity kappa. That's the equation on the top right. So that's composed of two parts, the lattice thermal conductivity and the electronic thermal conductivity. So the electronic thermal conductivity is L times sigma times T. L is a constant known as the Lorentz number. Sigma is the electrical conductivity. So that's hard to optimize. That kind of goes together with the electrical conductivity. However, the lattice part, kappa L, can be optimized somewhat independently. And that's the approach that many people have taken in recent years. So basically, what we're looking for is a so-called electron crystal phonon glass material. So it means a material which is highly ordered with respect to carrier transport. So it conducts electricity well, but is glassy with respect to phonon transport. So we want phonons which carry the heat through the material to be scattered easily and blocked from propagating long distances. Next, please. So schematically, this is the sort of approach that has been taken. Basically, we would like to nanostructure materials which have good electrical transport properties. And we want to nanostructure them on different length scales. So for example, you could introduce a high density of grain boundaries in a polycrystalline or ceramic material. So that might be at the scale of tens of nanometers up to microns. Then at the somewhat smaller scale, it's often nice to have nanoprecipitates of perhaps even a second impurity phase that spontaneously form in the material. So those might be on length scales of a few nanometers up to tens of nanometers. Then finally, on very small length scales, we would like to introduce perhaps point defects. So those might be from impurity atoms of various kinds. And with this nanostructuring on a wide range of length scales, you can scatter phonons of a wide range of wavelengths and thus prevent them from carrying heat through the material efficiently. That's what we want for an ideal thermoelectric material. Next, please. So this has been realized in a few materials. This is one well-known example in the literature. It's a chalcogenide known as LAST. That's the acronym for lead, silver, antimony, tellurium. So it's a well-known system. It has among the highest ZTs of about 1.7 for it's an N-type semiconductor. And on the right you can see some high-resolution electron microscopy pictures where there are nanoscale precipitates of second phases. They spontaneously appear in the material. They precipitate out, in other words. And they vary on length scales from just about 2 or 3 nanometers, that's the lower left picture, up to hundreds of nanometers on the picture at the top. So such nanostructures are very efficient at scattering phonons, while the electrical transport remains rather unaffected. So the mean free path of the carriers is only of the order of a few nanometers or even less, just a couple of unit cells in these systems quite often. Next, please. Now there's another approach which is being followed currently to optimize thermoelectrics, and that's to engineer the band structure, the electronic band structure of materials. So the idea here is to introduce so-called resonance states. And these resonance states, which are introduced by the dopant impurities, should be very close to the Fermi level of the material. So one well-known example is shown on the right here. That's lead telluride, which is doped with 1 and 2% of thallium. That's the ZT plot on the right-hand side. So the undoped material has a ZT of around 0.7, but if you dope it with 2% of thallium, the ZT more than doubles to around 1.5. And that's because there's a resonance state introduced near the Fermi level of the material. If you look at the electronic band structure, is a sharp increase in the density of states near the Fermi level. And that gives a great increase in the Seebeck coefficient, and hence in the ZT figure of merit. Next, please. So here's a summary from a review 2 years ago about some of the best performing thermoelectric materials that are currently known. So the best ZTs are currently around 2, both for N and P-type semiconductors. And if you can read the labels on this plot and see what these materials are, you may notice that many of them contain tellurium, so that although it tends to form good thermoelectric materials, it's not ideal because it's a very scarce element. And many of them also contain lead, which of course is toxic, and that's also not ideal. So it's kind of unfortunate that many of the best performing thermoelectrics contain either scarce or toxic elements. So there's also a drive to develop alternatives using earth abundant and non-toxic elements. So I'll talk a bit more about that later on. Next, please. So this plot here shows, it's a kind of plot of operating cost of a thermoelectric module for various general types of materials. So you can see from the plot that the operating costs are lowest on the right-hand side. That's for the highest ZTs. So those red symbols are for the chalcogenides. So those are mostly tellurides, sometimes selenides. So it's kind of unfortunate that we're stuck a bit with tellurides at the moment for the best performing materials. Next, please. So in our lab in Groningen, we've been working a little bit on various tellurides, and I'd just like to show some results of our own research pretty briefly. We've been working on this system here, which is known as TAGS. It's another acronym for tellurium, silver, germanium, antimony. So the chemical formula is shown on the top left here. It's a well-known thermoelectric. It's been known since the 1960s, and it is used in the Mars rovers currently. It's a good thermoelectric, among other things, because it has a complex domain structure shown in the electron microscope image on the left. It has this typical zigzag type of structure. Next, please. So the zigzag structure arises because of a crystallographic phase transition. So it goes from a cubic phase shown on the left, which is at high temperature, to a rhombohedral phase shown on the right, which is at room temperature. So the rhombohedral phase is formed from the cubic phase by stretching two opposite corners of the cube. So that breaks some of the symmetry, and you are left with a rhombohedral symmetry, which has a unique direction corresponding to the stretching direction of the cube. Now, of course, there are 4 body diagonals in a cube, so you can stretch it along any 4 of these diagonal directions, and this gives rise to the formation of these zigzag domains. So it's a naturally formed nanostructure which forms on small length scales of tens or hundreds of nanometers, and it scatters phonons very well. Next, please. So in the literature, it's been claimed that it's a simple phase transition from cubic to rhombohedral. This was reported by X-ray diffraction. Seemingly, you have a smooth transition. But we've looked at these materials again, and we've found that it's really not so simple, and there are some more complex effects going on. Next, please. So also, if you look in the literature at the thermoelectric properties that have been reported, without going through this table in detail, there are large variations between different reports of up to 30% in, for example, the electrical conductivity and the Seebeck coefficient. So it suggests that these samples are not all the same. People are not making the same TAGS phases in all these reports. Next, please. So we looked at the system carefully again, and we found that by carefully modulating the synthesis conditions, we can actually form different crystal structures of TAGS at room temperature. So by quenching directly from the melt, we form a kind of messy phase which contains mixed rhombohedral samples. This is often the method that's used in literature reports. And also, I think, by, for example, NASA in their thermoelectric modules. We found that if we use a more controlled cooling process, we can stabilize either the rhombohedral form or an apparently cubic form at room temperature. And these in turn have different structural and thermoelectric properties when we subsequently thermal cycle them, as would happen in a real thermoelectric module. Next, please. So we found, for example, that if we take the rhombohedral form of tags and heat it up, so these are X-ray diffraction diagrams, that it converts to a complex layered form of tags. It has trigonal symmetry and it has 40 layers. So there is one vacancy layer in a unit cell here, which apparently is on the germanium, antimony and silver site. That's a disordered site containing all three cations. And together with this we have the spontaneous precipitation of an impurity phase, silver 8, germanium, tellurium 6. So that spontaneously comes out of the tags phase when you heat it up. When you heat it up further to above 350 Celsius, the impurity phase redissolves again in the tags matrix. It disappears and the material becomes purely cubic. So the operating temperature range in a tags thermoelectric module is mostly in this intermediate regime where we have the spontaneous precipitation of the impurity phase. So this is likely helping to lower the thermal conductivity and gives us the good thermoelectric properties. Next, please. So a similar thing happens in the cubic form of tags, which hadn't been reported before. We again get, this time, an irreversible phase transformation to a different trigonal layer structure, this time with 21 layers. And this time it appears to have a tellurium vacancy layer, 1 per unit cell. And again we have this spontaneous precipitation of the silver 8 germanium tellurium 6 phase. And in this case it's irreversible. If we cool that back down to room temperature, we're left with the trigonal phase. And unfortunately the thermoelectric properties of this one are not so good as the rhombohedral one. But it shows that the structural properties of these tags thermoelectrics, although they've been known since the 1960s, are much more complex than have been previously appreciated. Next, please. This cubic phase at room temperature, although it looks cubic by X-ray diffraction, when you look at electron microscopy images, you still see the zigzag domain structure, which I think is impossible to have in the cubic phase. So this may be a case of X-ray diffraction only showing the broad average structure of the material, whereas on the local length scales it may be still rhombohedral, but this is still a bit of an open question and we need to investigate this further. Next, please. So this is what we think is happening. We have the spontaneous precipitation of an impurity phase, which leads to vacancies in the main tags phase. And as we heat them up, those vacancies become ordered in planes within the structure. And so we generate these new crystal structures with long C-axis and ordered vacancy layers. So this is similar to a previous report where vacancies were purposely introduced in a germanium antimony telluride phase. Next, please. One other thing you can do in the tags materials is to modify the electronic structure by chemical doping. So this has been reported in the literature for just 3 elements, cerium, ytterbium and dysprosium. And you can increase the performance by about 25%, and it's poorly understood why this happens. So these are dopants with magnetic moments, and it's thought that the magnetism of these dopants may have something to do with it. If you have magnetic moments in the lattice, you may favorably scatter the charge carriers in some way. But there's been very little theoretical studies being done on this, so it's unclear why it works. Next, please. So we've investigated a few other dopants in our lab, and we found that even greater increases can be obtained with vanadium and with manganese doping. So these are at just 1% levels, but we can obtain improvements in the efficiency by about 50% using these dopants. So we're still doing some experiments to confirm this, and we don't really understand why it happens. but these magnetic dopants seem to give great improvements. So that's an area, I think, which is very promising to explore in the future. Next, please. And for those of you who are interested in magnetism, we've also doped with iron. And here we obtain a ferromagnetic response at room temperature at low doping levels of iron. Of course, with iron, you have to be careful that the magnetic signal is not coming from the iron itself or from an impurity phase. We think that's not the case here, because this only works at very low doping levels of iron, at 1%. If you go to 1.5 or 2% doping levels, the ferromagnetic response disappears. So it appears this may be a way to generate a new sort of dilute magnetic semiconductor with ferromagnetic properties at room temperature. So again, this is ongoing research and something we have to investigate further. Next, please. So as I mentioned, using tellurides like tags or like some of the previous systems I mentioned is not ideal. Tellurium is one of the scarcest elements there is. So we would like to move perhaps to other chalcogenides if possible. Next, please. So in general, the 4-6 semiconductors are good thermoelectrics, so we can choose from germanium, tin or lead. Germanium is not good because although it's rather abundant, it's very expensive to process and purify, so it's a very costly element. Lead is toxic, of course, so it would be nice to use perhaps tin instead. And going to the chalcogenides, using sulfur or selenium would be preferable to using tellurium. Next, please. So actually this has been investigated recently, and the current world record holder of ZT is this material, tin telluride. So this has a ZT of 2.6 along one of the crystallographic axes. It's a very anisotropic material because it has a distinctive layered structure shown in the inset of the plot there. Now, although this has been reported as a world record ZT, there have been many groups who have tried to reproduce these results, especially in polycrystalline samples, which are favorable for large-scale bulk processing. But unfortunately, ZTs of only less than 1 have been produced in polycrystalline samples. So there's a lot of ongoing work there to see if this is really genuine. If so, it can probably be very usefully used as a bulk and a much cheaper thermoelectric material. Next, please. Other systems that have been investigated recently are a couple shown here. These contain mostly earth-abundant and cheaper elements. And these work on the basis that you introduce a certain crystal structure which has large voids in it, and it has so-called rattling atoms. So for example, in the scuttarudites on the left there, this is based on the cobalt antimony 3 structure, and you introduce a small amount of a certain other type of metal cation. And those are contained in large voids in the structure, so much larger than the cation itself. And there are large thermal vibrations of these atoms. That's why they're called rattling compounds. And this again helps to scatter phonons and lower the thermal conductivity. A similar process occurs in the clathrate group of materials that's shown on the right there. For example, barium-8, gallium-16, silicon-30. Again, all cheap materials. ZTs of approaching 1 have been achieved here. And here again, the barium cations are enclosed in large cages in the crystal structure, and they're able to have large thermal vibrations and rattle around. Next, please. Another similar material is the tetrahedrites. And here, although there are not really large voids, there are copper cations, which are shown in blue on the left-hand side, and they have a unique coordination by 3 sulfur anions. And these copper cations also are allowed to vibrate with a very large amplitude perpendicular to the plane of these copper S3 units. So again, this helps to scatter phonons. And these tetrahedrites, which are sulfides, they're also achieving ZTs of around 0.7 in the latest results. Next, please. One can also go to silicides, so those are the materials we're using in the prototype modules with Tata Steel. So these are incommensurate crystal structures where we have a manganese sublattice which does not exactly match the periodicity of the silicon sublattice. So you cannot describe these materials with a conventional unit cell. So in a way you have a sort of disorder from the mismatch between the two sublattices. And this again gives rise to good phonon scattering and good thermoelectric properties. You can make these manganese silicides on a large scale and very cheaply. So what is done by Tata Steel is they grow large thin plates of the materials, and they can build energy harvesting modules on the meter squared scale. So they're very cheap materials, and although ZT is only around 0.5, they can still get a lot of their waste heat back, which is otherwise just lost. So they're interested in any kind of cost savings they can get. So these types of materials may be useful for any large-scale industry which has a lot of waste heat. Next, please.
I'm sorry, 2 minutes left.
2 minutes. So just very quickly, oxides are also of interest, especially the best performing oxides have ZTs approaching 1. And they usually have triangular lattice structures with the so-called cadmium iodine 3 structure. So the prototype is sodium cobaltate. That's the best performing oxide by far. Next, please. And this is a similar material that we've made in our lab. It's a new material containing rhodium. And again, it has a similar triangular lattice of the transition metal rhodium oxide. And sandwiched in between the rhodium oxide layers are, in this case, barium oxide layers, which don't exactly match. So again, you have a mismatch of lattices and disorder and good thermoelectric properties. Next, please. So just quickly, I'd like to show a couple of possible future directions. One being talked about the inorganic-organic hybrid perovskites, which are well known as solar nacelle materials. There are also some predictions shown on the right that they're good thermoelectrics. What one has to do here is dope them, though, to get a high enough carrier concentration, and that has not been successfully done yet. Next, please. And the other possible systems are perhaps hybrid systems containing inorganics in a conducting organic matrix. So, for example, in a conducting organic polymer. And those are materials we're beginning to look at in Groningen nowadays. For example, with inorganic quantum dots. Next, please. So just to summarize what I've gone over in the talk, and what is my opinion of the current state of thermoelectrics. Currently, chalcogenides are still the best materials, and we need to find alternatives to replace tellurium and toxic lead. So there is a lot of progress on many different material systems being made. Oxides may have a future. They're generally cheap and easy to synthesize, but they're still far behind chalcogenides in terms of performance. And actually, in the future, hybrid systems may be best, containing a combination of inorganics and cheap, easy, low-temperature processable organic materials. Next, please. So I'd just finally like to thank my collaborators listed here, and I'd like to thank you very much for your attention.